So I've been putting this off for a while, and we're now finally getting to what I've been talking about, this precise definition of a limit. But before I do that, I want to remind you a little bit about a couple of things. And this week, teaching my college algebra class, I came across this example that we'll see in a minute. And I really liked it. I loved it. I was like, oh, this is kind of like what you'd be doing in calculus when we're manipulating things to look like what we want, which we'll be using today. So just to remember, because we're going to be using this fact, if you have the absolute value of some expression, so let's call it u, is less than, you could have the equal to piece in there too, some constant k, really our value has to be greater than or equal to 0 or it won't hold true. If your constant was negative, you can't have an absolute value of something which is positive to be less than 0. Okay, so if that's true, we can drop that absolute value by sandwiching in between the negative of that constant and the positive of that constant. Okay, so this example that we have here, we're given that the absolute value of x plus 6 is less than, or sorry, x plus 2 is less than or equal to 6. Then we're given that a is less than or equal to 2x minus 6 is less than or equal to b, and we want to find a and b. So the whole goal here is to get what's inside this absolute value equation, this x plus 2, to look like the middle of this compound inequality, this 2x minus 6. So we want to not have absolute values, and we can use that rule that we can drop the absolute value if it's a less than or equal to by sandwiching it into the negative and positive of itself. So I can rewrite this as negative 6 is less than or equal to x plus 2 is less than or equal to 6. So I want a 2 in front of my x, and I want to be subtracting off 6. And so you got to kind of think to yourself, what can I do to manipulate that? Well, one thing that we can do in order to get that 2 in front of the x, we can multiply every single side by 2. It's a positive number, so that doesn't change the direction of my inequality, so I'm okay. And so I have 2 times negative 6 is negative 12 is less than or equal to, let's distribute that 2 inside the parentheses inside the middle of the inequalities. We get 2x plus 4 is less than or equal to 2 times 6, so positive 12. So we've gotten that 2x where we want it, but we really want minus 6. We don't want plus 4. So let's just think to ourselves, what can we do to get a minus 6? So think to ourselves, what can I subtract off of 4 to get negative 6? Well, I know if I subtract 10 from 4, that's negative 6. So let's just subtract 10 from all these sides. So that would give us negative 12 minus 10. So that's going to give us negative 22 is less than or equal to 2x minus 6, which is less than or equal to 2. And so we wanted to know, what is our a value? Well, our a value is what's going to be in the left, because we got what's inside to be the same. So a in our case is equal to negative 22. And our b value is what we have over here. Our b value would be 2 in order for that to hold true. So in just a minute, you'll be seeing that we're going to be using this concept to be able to manipulate what's inside of that compound inequality, that expression, to look like some other expression. Okay. Let's let you guys have a moment to finish writing that down. Pretty much all semester, we've been looking at limits, how to find limits algebraically, how to find limits by looking at a graph. And the definition that we've been using right now, before this precise definition of a limit, we've been saying if y value of a function f of x becomes close to a single value L, as x gets closer and closer to a point C, from both sides on the left and right, then the limit of f of x as x approaches C is L, which can be written as the following mathematical notation. So that limit with the x with the arrow below goes to C, f of x is equal to L. So we've been kind of using this definition of getting closer and closer and closer, getting really close. And that is basically what we're doing, but let's get a more precise definition mathematically of how we can write this. Okay. So in this section, we're going to be looking at the precise mathematical definition of the limit that we had looked at earlier in this chapter, which we just went through. And so now let's read through how to find the precise definition of a limit, and then we'll intuitively look at what's going on the graph. Okay, so the formal definition of a limit, it says let f of x be a function defined on an interval that contains some value a, except possibly x equals a, because remember, didn't necessarily, if a limit exists, it didn't necessarily have to exist at that a value or that x value. Then we say that the limit as x approaches a of f of x is equal to L. If for every epsilon greater than 0 is some number delta greater than 0, such that the absolute value of f of x minus L has to be less than epsilon, whenever 0 is greater than the absolute value of x minus a is less than delta. Okay, so that's a lot of words there, and let's just kind of break down what it means. So let's look at this graphically for a second. So I have a picture in front of us of some arbitrary graph. Okay, so we're looking at some x value a. So let's just put a on this graph. So let's say that this was value of a in here. So if I look at this, right, if I go up here onto my graph, that value that I'm hitting on the graph, right, as I get closer and closer to a, this value in here, this is my y value of L. If we can say that there's some epsilon, so let's say that we're blowing this up because we're getting really, really close, and normally our epsilon is very small. So let's say that there's some epsilon. So epsilon is some constant that we can either add to our y value of L, or we can subtract from our y value of L. And so basically this value in here, this right here, this would be L plus epsilon. And this right here, this is going to be the y value L minus epsilon. Then we know there's some delta greater than 0 such that that y value, f of x minus L, is less than delta, epsilon, whenever x minus a is less than delta. Basically, if I kind of map this back to where my x value would be, I have some point in here. And if I mapped this value back in here, I have some value in here. It's not necessarily that the distance on the left and right of A is the same. So basically, this is saying if we have some value, we're going to find some delta that's always going to get us in that neighborhood of L minus epsilon and L plus epsilon. So technically, we want our delta value. So maybe let's call this distance 1, because I don't know if that distance in here, distance 1, is the same as distance 2. And let's call this here distance 2. And so delta has to equal the minimum, whatever one is smaller, of the set, either that distance 1 or the distance, that value of our distance 2. Okay, so once we found that smaller distance, that's basically saying, okay, if I choose my x value in between this a minus delta and a minus, so a minus delta, we know is less than a plus delta. If I choose an x value that's in between here, I know that I'm gonna, excuse me, fall inside that neighborhood in here. So if I chose a point right here, right? If I go up into and see where it's hitting the graph, it must hit inside this epsilon. So any value we choose in here, we're gonna be able to show that it's in between this L minus epsilon and L plus epsilon. So kind of, it's helpful sometimes if you just look at, like I had done with the horizontal vertical lines. As long as we're in between these values, we're good. Anything you chose in between here is going to be mapped back over here. Notice if we chose some value outside. So let's say I chose something out here, my x value out here. Well, that's outside of that delta, a plus delta, a minus delta. And notice if I map this back up to see what the limit is or what my y value is, that's definitely getting outside of that interval. And so that would be too big. So this is definitely applicable to real world. So let's say you went to the lumber store and you were buying a piece of wood or 2x4 piece of wood. When you buy that 2x4 piece of wood, my guess is that every single piece that you buy is not exactly 2 inches by 4 inches. There's going to be some little bit of room of error. It's impossible to get them all exactly the same size. And my guess is that there's some room for error. If it was a half an inch off, that would be too big. They wouldn't like that. But maybe if you're like 0.0001 inches off of it being exact, they would say, okay, this is good enough. Same thing could deal with weight. You're looking at a weight of some product you're buying at the grocery store, chips or something. They tell you on the bag how much that weighs. Well, there's probably some little bit of error that is available in there to say, okay, well, this is approximately very good enough to be the amount of ounces that it told us to. So let's look at some examples, and hopefully with the examples, and I'm going to kind of start off smaller, we'll get bigger, this concept will resonate with you. So I pulled some stuff similar to what you'll see on the homework. So let me just make this a little bigger. So the first example, it tells us to sketch the interval AB on the x-axis with the point C inside, and then find the largest value of delta greater than 0 for all x, such that 0 is less than the absolute value of x minus c, which is less than delta, implies that a is less than x, which is less than b. We're given here that a is -5/9. We're given that b is -1/3, and we're given that c is -1/2. So first thing they just want us to do is graph this. And so if I was to graph this, right, -5/9, I'm just gonna, we're blowing this up, and this is not necessarily to scale. So -5/9, let's say this was -1/3. And let's say that this is -1/2. And so we're looking at all the x values that are between -5/9 and -1/2. It wants us to figure out what is the largest value that delta can be. So basically, we want to find the distance. We need to figure out what is the distance between that endpoint -5/9 and our c value of -1/3. So you can look at the absolute value of, because absolute value is always positive, -5/9 minus -1/3. Or -5/9 minus a negative is plus. I notice in order to be able to add these are fractions, I need a common denominator. So let's just multiply this 1/3 by 3/3. So that would give me plus 3/9. And that would give us -2/9, but the absolute value of -2/9 is 2/9. So this distance in here is 2/9. And now we want to find the distance between -1/3 and -1/2. So again, I can look at the distance. So -1/3 minus a -1/2, or I could have said -1/2 minus a -1/3. Absolute value of that result. So I'm going to need a common denominator. I know that this is the same thing as -1/3 plus 1/2. 6 is my common denominator. So this is -2/6 plus 3/6. This is equal to 1/6. which equals 1/6. Let's see something real quick. Yikes, I made a mistake. See, that value -1/2 has to be in between. And so this is actually wrong, unfortunately. So let's rewrite this. I'm just going to move these over, but my distances are off because of that. So the -1/2 is in between -5/9 and -1/3. So this right here is -1/2, and this is -1/3. And so that first distance that we looked at, this is the absolute value. Again, we can write it as -5/9 minus a -1/2. But I need a common denominator. So 9 and 2 to get our common denominator is going to be 18. So I'm going to multiply this first fraction by 2/2. A minus and negative is plus, and I'm going to multiply 1/2 by 9/9. And so we have absolute value of -10/18 plus 18/18 is 8/18. And that reduces to 4/9. So this distance in here is 4/9. And now we want to find the distance in here. And so we have distance here, distance 2, let's call it. That's the absolute value of -1/2 minus.
Be 9/18, not.
Yeah, wouldn't it be 9/18?
8/18. Yes, what did I do? Because I wrote that as 18/18. I need to slow down. Thank you guys. So this should have been 9. This would have given us then absolute value of -1/18, which is equal to 1/18. So this is equal to 1/18. Thank you for stopping me. Distance 2. So -1/2 minus 1/3. So we're going to need a common denominator. So this is -1/2, but my common denominator is going to be 6. So I'm multiplying that first fraction by 3/3. And that second fraction, I'm going to multiply by 2/2. So I get the absolute value of -3/6 plus 2/6. This is equal to -1/6, which is equal to 1/6. So we want to choose delta. To equal the minimum of those two distances that you found. So whatever is smaller, either 1/18 or 1/6. So when you're comparing fractions and seeing which one is smaller, sometimes it's helpful by rewriting them with a common denominator. I noticed that 1/6 is the same thing. If you can't see it. This is the same thing as 3/18. And 1/18 is smaller than 3/18. So we're going to choose delta to equal 1/18. So choosing the smaller of the two will ensure that when we map back up to our graph, that we're going to be inside that epsilon neighborhood of our limit. Okay, so our next example, we're given actually a picture of a graph, and it says use the graph below to find delta, a delta greater than 0, such that for all x, 0 is less than the absolute value of x minus c, which is less than delta, gives us the fact that f of x minus L is less than epsilon, that distance. So same kind of idea that we were just given. We want to figure out what delta is. And delta is going to be the smaller of these two distances. So we have either this distance here between 49/64 to 1, or we have this distance here between 1 and 81/64. So we're going to choose delta to equal the minimum of those two distances, delta distance 1 or distance 2. Okay, so distance 1 we can find by taking the absolute value between 1 minus 49/64. Common denominator, 1 could be rewritten as 64/64 minus 49/64. Well, 64 minus 49 is 15 all over 64. Okay, so we have delta is either equal to the minimum of 15/64. Let's look at the distance 2. So if we go from 81/64 minus 1, the absolute value of that, 81/64 minus common denominator, 1 could be written as 64/64. 81 minus 64, that's 17/64. So minimum 15/64, 17/64 is going to be 15/64. So delta would have to give us 15/64. So we would have to shrink this piece over here. And we could figure actually out what the bounds would have to be, right? If I added, I know I need to add my distance 1 here. So if I add 15/64 here to my 1/1, that would give me 71/64. 15 plus 64. That would give me 79/64. The problem would be if I had chosen it to be the bigger one, what would have happened is that would have put me a little bit outside over here. If I had made this to be 17/64, if I had subtracted that from 1, that would have given me values outside of this interval. Notice if I chose something over here and I went up, that would not bring me inside of my delta or my epsilon neighborhood. And so that's outside. And so that's why we have to choose the smaller of the two distances to guarantee that any number we choose in between a minus delta and a plus delta, that would get us into this neighborhood in here. So all those examples that we just went through was to work us up so that we could be able to do this for any problem. And so I'm gonna walk you through the steps on how to do this. First example, and the linear functions are a little easier than functions that aren't linear, but show that the limit as x approaches 4 of 2x plus 3 is equal to 11. And so let's just talk about it really quickly. If we went back in, right, and did our direct substitution and we plugged in 4, wherever we saw an x there, 2 times 4 is 8, 8 plus that 3 is 11. So we know by direct substitution that we would get back 11. But let's prove this using the delta epsilon proof. And so I threw back in here what that said, and that said that if you're looking at the limit as x is approaching a of f of x equals L, if for every epsilon greater than 0, there's some delta greater than 0, such that distance from the y value plus L minus L is going to be within that epsilon. Whenever 0 is less than x minus a is less than delta. So really the first thing that you want to do when you're solving these is let's write this out. So determine in our example, what is our a value? Well, our a value is what we're approaching. So the value that we're approaching in this example is 4. So a is 4. Our function that we're taking the limit of is the 2x plus 3. So f of x is 2x plus 3. And L is what our limit is. And L in our case is 11. So let's go and rewrite. Plugging it into the absolute value of f of x minus L is less than epsilon with what we had just said those values were. So we have the absolute value of f of x, but f of x, remember, is 2x plus 3 minus my L value, so minus 11. That absolute value is less than epsilon. Whenever, so 0 is less than the absolute value of x minus, well, let's go and see what our a value is. Our a value was 4, so minus 4, which is less than delta. Okay, so this is where we're going to kind of use that trick I was showing you at that first example. So we're going to first play with this f of x minus L. That absolute value is less than epsilon. And our goal is to manipulate that to look like what's inside the absolute value of x minus 4, in our case, x minus a, and generically. So we're going to take this piece right here. So I have the absolute value 2x plus 3 minus 11 is less than epsilon. Sometimes they're going to tell us what epsilon is, how close we want to get. In this case, it didn't tell us what epsilon is. So let's first simplify what's inside our parentheses. So we got 2x, well, 3 minus 11, so that's minus 8. That absolute value is less than epsilon. So I'm trying to manipulate this to look like x minus 4. Notice that 2x minus 8, they both have a factor of 2 in common. So we can actually pull a 2 outside, or let's just first pull it out of the 2x minus 8. So that is absolute value of 2, parentheses, x minus 4, and our parentheses absolute value less than epsilon. But isn't 2 a positive number? And so since 2 is a positive number, we can pull that outside of our absolute value symbol. So it's the same thing that 2 times the absolute value of x minus 4 is less than epsilon. So we have what we wanted to inside the absolute value symbols. We just want to get rid of the 2. And so we're going to say that the absolute value of x minus 4 is less than, let's divide both sides by 2, epsilon over 2. So once you've manipulated it to be what we wanted, which we did, we're going to choose delta to be what we had gotten on the right-hand side of our inequality above. So in our case, our delta, we're going to choose to be epsilon divided by 2. So we've actually figured out what we're going to choose delta to be. We kind of worked backwards, and now we're going to, this is like our scratch work of our proof. So we're going to start in the opposite direction. So we chose what delta has to be. And now we're going to work backwards. We're going to look at what we have for the absolute value of x minus a is less than delta. But in our case, right, that should be a delta, not an a. This would be x minus, our a value is 4. That absolute value is less than epsilon halves. And now we're going to do the same thing we just did above, but going in the opposite direction. Now we want to manipulate our inequality to look what we originally started with. Well, I can see that we can get that, right, by multiplying both sides by 2 to clear that fraction on the right-hand side. So that would give me 2 times the absolute value of x minus 4 is less than epsilon. It's a positive number that we're multiplying to the absolute value. So it's the same thing as pulling it in and bringing it inside the absolute value. So this is the same thing as 2 times parentheses x minus 4 is less than epsilon. So 2x minus 8 is less than epsilon. Recall, we're trying to make it look like, so go back up and see what we're trying to make it look like. We're trying to make it look like this 2x plus 3 minus 11. 2x plus 3 minus 11. Well, negative 8, right? That can be rewritten. So 2x minus 3, or sorry, plus 3 minus 11 is less than epsilon. This is our f of x value. This is our L value. It's less than epsilon. So we chose some delta to equal the half of what epsilon is, and that will guarantee us that we're going to fall in that epsilon neighborhood. Okay, so here's an example with some real numbers or a value that we want epsilon to be. So for the given function f of x and the values of L, C, and epsilon greater than 0, find the largest open interval about C on which the inequality f of x minus L is less than epsilon holds. Then determine the largest value for delta greater than 0 such that 0 is less than x, the absolute value of x minus c less than delta gives us that f of x minus L is less than epsilon. Okay, let's look at this. That's where we're going to start. F of x we're given is 2x plus 3 minus my L value, so minus 21 is less than, well, epsilon in our case is 0.12. And for our delta piece, we have 0 is less than the absolute value of x minus c, c in our case is 9, is less than delta. So our goal is to get what's inside this absolute value to look like x minus 9. So I normally start with combining like terms inside my absolute value. And so doing that, we have 2x, well, 3 minus 21, that gives me negative 18 or minus 18 is less than 0.12. Same sort of kind of idea that I had done in the last one. I can pull out a 2 from 2x minus 18. I actually can pull it outside here. So factoring out a 2, it's positive. I can pull it outside the absolute value. So 2 times the absolute value of x minus 9 is less than 0.12. Let's divide both sides by 2. So x minus 9 has to be less than, well, 0.12 divided by 2 is 0.06. Okay, so we're going to choose delta equals 0.06. And so it wants to know what is the, I believe, the interval. So then determine the largest value delta greater than 0 such that this is the case. So we did. Find the largest open interval about C. Okay, so we haven't done that. Find the largest open interval around C. Our C value is equal to 9. So I need to look at C minus delta. So this would be 9 minus 0.06. Which would give us what, 8.94. And we need to look at C plus delta. So this would be 9 plus 0.06, which would give us 9.06. So that interval, the neighborhood of our delta, that 9 value has to be between 8.94 and 9.06. If we choose any X value in there, it should map us into the epsilon neighborhood on that y-axis. Okay, so I'm going to go through one more example. In this example, it's not linear, so it's a little more difficult, but it's not too bad. In this example, it says for the given function f of x and values L, C, and epsilon greater than 0, find the largest open interval about C on which the inequality, the absolute value of f of x minus L, that's less than delta holds. Sorry, less than epsilon holds. Then determine the largest value of delta greater than 0 such that 0 is less than absolute value of x minus c is less than delta, gives us then absolute value of f of x minus L is less than epsilon. Okay. So we're going to start with looking at the absolute value of f of x minus L is less than epsilon. And so our f of x value is the square root of 8x plus 81 minus my L value, which is 11. I want this less than epsilon, which is 0.01. I also want to look at what I'm trying to aim for. And so I'm looking at x minus c less than delta. And so c in my case is 5. So x minus 5, that absolute value is less than delta. Okay, our goal. Our goal is to get what's inside this absolute value to be the same thing that's inside this absolute value. So let's start by actually dropping our absolute value. We have a less than, and we can drop that by sandwiching it in between the negative of 0.01 and the positive 0.01. Okay, so notice that we don't have any radical when what we're trying to get to. And so let's clear that radical. And in order to clear it, I know I'm going to want to square everything. And I can't do that until I get rid of that minus 11, or I'm going to have some mess in there. So let's get rid of the minus 11 by adding 11 to each side of the inequality and in between. So 11 minus 0.01, that gives us 10.99, is less than the square root of 8x plus 81, is less than 11 plus 0.01 is 11.01. So I notice that I can get rid of the radical by squaring each side, and squaring things are, you're multiplying it by itself. Those are all positive numbers, so it's not gonna change the inequality. So that's legal. We can square each piece. And so we have 10.99 quantity squared. That's going to give us 120.7801 is less than 8x plus 81, which is less than. So if I take 11.01 and I square that, I get 121.2201. So I want x minus 5. And so let's get x by itself in between, and then we can manipulate it to get that minus 5 there. So what about, let's subtract 81 on all sides. I'm going to do it on the right-hand side first, just because I already have that in my calculator. And so on the right-hand side of that inequality, 121.2201 minus 81 gives us this 40.2201 is less than 8x is less than, so 120, let me just see if I can do this in my head, 19, that's going to be 39.7801. Got to get everything by itself, right? Or get rid of that 8 in front of the x. So let's divide everything through by 8. Again, I'm going to start with the number on the right hand, far right, because I have that one in my calculator still. And so dividing that answer by 8, I get 5.0275125. And 39.7801 divided by 8. That would give me on the left-hand side 4.9725125. I'm almost there. I want x minus 5. And so notice that if we subtract 5, from each piece, so if I subtract 5 from the first piece, I'm left with negative 0.0274875 is less than x minus 5 is less than. So subtracting 5 on the right-hand side, far right-hand side, we get 0.0275125. And we want the minimum distance. Let's think about this. So we want the minimum. So let's look at actually the absolute value of 5 minus this 49 point or 4.9725125. Let's see if I wrote this down right. 125. Okay. That's going to give me 0.0274875. Where if I look at the distance of 5 minus this value right here, 5.0275125. That gives me 0.0275125. I want to choose it to be the smaller of the two. So minimum of those two distances. And I'm just going to call it distance 1 and distance 2, so I don't have to write those decimals in there again. And so looking at the smaller of the two, I got to look at them. It looks like the first distance. It would be distance 1. That decimal is smaller. Is this 4 here and this 5 here, 4 smaller than 5. Let me just make sure I answered it. So forget the given function. Find the largest open interval about C, which the inequality, okay. Then determine the largest value of delta. Okay, so we found the largest value of delta. That interval around C, we're going to get it by adding it to 5 and subtracting it from 5. So 5 minus the distance 1. Well, we already got that. That was the one right here. that was that. It's going to be 4.9725125. And 5 plus that distance of delta. So that would give us 5. 5 plus this decimal is 5 and the decimal. So 5.0274875. So that's our largest interval around C that would map us inside of that epsilon neighborhood. Let me stop there. And so this is all of 2.3. I just want to reiterate, and I mentioned this throughout the semester. So this delta epsilon proof, this precise definition of epsilon, it's a little bit abstract, and hopefully I've kind of explained it so it's not as abstract. I know I struggled with it when I first went through college, and this is one of the things in this class I always get a little bit of anxiety about coming and talking about, but it's getting easier and easier as I teach this topic. So don't stress out if you don't really understand this. It's not going to ruin your career in calculus, and we'll get past this right away from this kind of more abstract thinking and get more into intuitively what's going on and finding the work.